Okay, so we proceed with the next presentation. Last in our track, before we come to the main and common key presentation. Last one we have here from Siemens Healthineers, Marius Klemm, was working hard and intensive on simulation topics, and he wants to share with us some results on Stub simulation, on the design, and will share with us the results. Thanks, and please welcome him and on stage.
Yes, so hi, thank you that you are all here, and a great welcome from me. So I am Marius Klemm from Siemens Healthineers, as you heard. I am a PCB layout designer and also simulator. So I'm doing simulations for high-speed designs, so digital high-speed designs, especially using the whole Mentor toolchain and hyperlinks. And so before we get into this talk right here, I want to explain or give you an image of how we at Healthineers want to incorporate the PCB design into a digital twin. And the major point that I can contribute into this for high-speed design especially is giving a precise and accurate simulation model of the PCBs regarding signal integrity and power integrity. And since there are many challenges in these areas and in these fields, we always need to look out to not over simulate and over engineer everything and re-engineer every issue and every new PCB that we have from scratch. So what we want in the end is a digital twin, but as efficient as possible to get there. So the main goal for us is to first off understand our problems that can cause signal integrity issues, and then if we understand them, how can we find rules? How can we find the behavior? And how can we bring this from the end, from simulation, or even if an error occurs from measurement, how can we understand it and how can we draw conclusions back into the beginning, into the first place of constraining or DSC checks? And so this is one example. It's for stubs, what they do with the PCB, with the high-speed channels, and this approach is more and more getting done in our team. So the topic right here is accurate stub simulation especially in hyperlinks using all kinds of solvers that are available. And I'm trying to, in this regard, I'm trying to optimize the mesh parameters, the solvers, and also have a look on what do I have to expect from manufacturing variations, tolerances. What is my PCB? What are the effects on my PCB? Yeah. So at first I will start with a small introduction on what is a stub and why does it cause signal integrity issues. Then we go through some parameters from meshing, solver, and manufacturing. And in the end, I will give a simulation to measurement correlation where we did 3 channels, processed them, manufactured them, and then measured them, correlated to the optimized parameters. And then we see that it's what we need for good simulation. Yeah. So first of all, before we start, what's my typical simulation and measurement setup? In the first place, what I try to do is I knew that I was going to optimize the meshing and the solving part. So especially in the 3D area with the full-wave solver, which takes a lot of time, we wanted to incorporate or to use the job distribution and to also use HPC for high cluster computing. It wasn't ready up to now. We are still in very good support, or we're getting still very good support from Siemens EDA and hoping to get this built up. But up to the state where I made this presentation, we weren't ready yet, and so I used my own laptop working horse laptop. For the measurement, we're using a Rohde and Schwarz VNA up to 40 gigahertz. That's what I also simulated and measured. What I am showing here is only up to 30 gigahertz because it's the most interesting range that the effect is gonna happen in this case. We use calibration kits, very clear compression mount connectors up to 40 gigahertz. And for simulation tools, we're using all that Hyperlinks gives us. So the simple 2D solver models, hybrid solver, and especially the full-wave solver. Also, we're using the entire matchup, like match boundary, frequency-dependent dielectric models, surface roughness, etching of traces, and also adaptive frequency sweeps. So, coming to the actual problem of via stubs, for example, to show this effect, I created two simple channels. The first one on the left is a short PCB trace, the same as on the left one. The only thing is this stub is represented by a transmission line, for example, here, that is not in the signal path. So it's a stub outside of the signal path where the signal wouldn't or shouldn't travel through. For vias are drilled through, and you connect to both layers or to two layers, and most of the times you have a remaining stub in the via. And this is a very short modeling of this. And what we see here on the left is a single stub, but it's long. On the right, we see two stubs, but they are shorter. They are half the size. And what we see is the single stub is more critical to the eye density or to the eye area than if you have two stubs, but with a smaller stub length. And this is quite interesting. Then the next question is, why is this the case? What we see here is the insertion loss of our channel. So the power that I'm sending in, how much, at what point of frequency, how much power am I getting out? What I want is the curve to be as high as possible. That means all the power I send in is coming out. And if we have these drops in the middle, for example, that I'm gonna explain in a minute, then we have it's like a power suck out, or these frequency, the power is attenuated extremely strong. And so these frequency will be blocked. They will reduce our rise time in the digital time frame, and this will make the digital signal flatter. This is what we saw in the last frame. And now to compare the both channels, what are the insertion losses? The channel and the eye diagram on the last slide was PCI Gen 5, for example, where we have a Nyquist frequency at 16 gigahertz and a third harmonic, which would be then the appropriate bandwidth of our signal, is around between 45 and 50 gigahertz. And what we don't want is any resonance within this area, because within this area there's a main signal energy. And what we have is the orange line tells us this is the channel with the with the single long stub. We have a long stub which causes a resonance quite early in the frequency range. If we have multiple but shorter stubs, the resonance will appear far more right, sorry, which is better for us. Yeah, it's not as critical. So your target is also, or what you can say is, if your signal bandwidth goes up to here, you don't want your resonance inside there. And in most cases, you can determine some value somewhere around here to be, this is my channel bandwidth. And then you can compare these two values in frequency domain. And the target is to have your channel bandwidth greater than your signal bandwidth. Then you are fine. All right. This is one example how to solve this in hyperlinks. This is a channel that I built, which we also had a measurement for. On the left and right, you see the attachments for compression mount connectors, a microstrip connected through it, which was like 1.5 centimeters long strip, and then a full THT via drilled through it, which represented the entire stub. And what we see right here is the orange line comes from the simulation out of the 2D solver. So the simple, no actual solver in hyperlinks, it's just selecting the trace, solving it, then you get this result. It's resonating at 6.5 gigahertz. When we use the hybrid solver, we are landing about, the hybrid solver is the black one here, it's like 10.5 gigahertz. And if you compare it to the measurement is sitting at 13 gigahertz. So we are only reaching like up to 80% of accuracy with the stub resonance, which is characteristic. And then the question is, how do we get even closer? Because we want to create a digital twin that is very accurate, and we don't want to simulate over and over again. So we want to learn from it to prevent it in the first place. And if we do this simulation and this effort in our simulation and this time, we only want to do it once. But if we do it, we want to make it accurately. And then it's a question, okay, we have to use the fullwave solver to solve this. And in this case, I'm going through parameters that are relevant, very relevant for this fullwave solver, yeah, to reach this resonance. So these are not, this is just a different channel. So this is just a very small channel, only a via stub. And there I'm only changing one parameter at a time. And this is where we go through right now. So the first parameter is inside the mesh. You can define, if you look on top of the PCB, you can define your circles in different resolutions. So this is called the number of arcs in hyperlinks. If you're using 6, you have 6 edges. If you're using 12, it's getting more round, but also makes the meshing more dense and gives a higher resolution. But the question is, do you need that resolution? Yeah. What we see on the left, insertion loss again, the deviation between all these three is very little. So on the right, you see also on resonances, there's not much deviation. The only thing that's really increasing a bit is the time that we need to simulate for each frequency point. So in the beginning, it's 4 minutes for the 6 edges, and then we have 5.8 minutes for 12 edges. And for me, I thought, okay, depends. 6 would be nice. Okay. The time increasement is okay for us if we take 10. If you take 8. And the resolution can be a little bit more better if you're using multiple stitching vias for ground, or if we're having more complex structures within this area, then 8 would be a good parameter to use it for. So the next effect was, or the next value is the cells per wavelength. This means if I'm simulating up to 40 gigahertz, 40 gigahertz is a very short wavelength. And within this wavelength, I want to pack either 5 or up to 50 cells of my mesh. And that means you see on the left one, this is 5 cells per mesh. And on the right one, you see 50 cells per mesh for each layer. So the mesh kind of explodes. And the question is, mesh explodes, the simulation time explodes or increases. And what does it do to a frequency response? Almost nothing. Yeah, but still to go, the value for 5 is quite on the, yeah, it's really, really on the edge. So what I expected, or what I can recommend, is a value of 10 to be precise. In other cases where it's a more complex 3D structure, then you are still better going with this. Then the next parameter is what we can do in the mesh is simplification. This was just for interest, because our goal is to find the stub resonance, but you can also disclude the stub resonance. as well as this stub awareness. Yeah, you can also disclude non-functional pad awareness. I will come to this later. Yeah, but these two options are available. I just wanted to check how much difference is there. What does it make here? So in the resonance, we see a big deviation from 13.2 gigahertz to 16.8 gigahertz, so a large deviation. But we're also using only the half of amount of time in that case. The problem is we're losing very much accuracy, which we want to have. So not recommended to deactivate these settings. So this is like for the measure. Then we're coming to the solver. In the solver settings, we have the major setting is the accuracy slider. This accuracy slider, mainly it has a grading from 1 to 7. And the main differences are from one to the other is edge meshing. So the first one is the lowest setting. And from 2nd to 7, you have edge meshing applied. And each step further only increases the sensitivity for crosstalk, which in our case wasn't relevant. So my recommendation was getting it with 2, because what we see in the frequency domain is accuracy slider number 1 is off all the others. So edge meshing does have an effect, should be included. Next one, since we are through with meshing and solving, what we want to now analyze is the variations from the manufacturing side. And the first one is, for example, a dielectric constant. We try to simulate things in the first place and then manufacture. And that's why I had 3 rules of thumb. So the first one is the typical, you use a material data sheet, take these values and simulate. The next one is typical in PCB design, where you subtract 0.3 from the dielectric constant. And then there's another one which is upcoming in the latest years. It's called the anisotropy, which is, the reason behind that is it's larger for the via than for a transmission line, because the transmission line in the PCB is the electric field in the transmission line is directed into the C direction, so to the bottom through the PCB. And for a via, the electromagnetic fields are getting out of it, so in the XY plane. And this is due to FR4 inhomogeneity. We're having some anisotropy, so some different material behavior. And the typical factor here is 18%. That's what the latest research gave. And this is also just a rule of thumb. Look, what does it do to our resonance? And what we see is we still have a difference between like up to 1 gigahertz into plus minus range. Yeah. So there's a difference, and you always need to, if you like, this is interesting if you're doing measurement to simulation correlation, because if you are in your simulation off the measurement, you maybe it's the case of a dielectric constant, yeah, which you want to adapt. So, but in the first place, I would start with a data sheet for simple terms. Then the next parameter is also the drill diameter, which is very interesting, because what often happens, and what we recognized, was that our PCB vendor may understand something differently than what we give him. So we are designing, for example, PCBs with a drill of 0.2 millimeters. And either the PCB vendor can think, okay, I have to drill with 0.2 millimeters, which is the orange curve, which has a finished hole size. So after plating, it's an even smaller hole. But he can also, the typical case is in the middle. He knows that it's finished hole size. He will drill a little bit bigger, so 0.25 millimeters, and add plating to reach the 0.2 millimeters in finished hole size. It's the black curve. And then there's also cases where the PCB vendor in thick PCBs or for higher IPC ratings, for example, you need more plating thickness, and then he needs to drill thicker. And The problem is you see the effect. It's almost 1 gigahertz in the effect of the stub resonance, and this is something that you have no control over, but you should have control over it. And that's very interesting. So you need to get in touch with your PCB vendor, need to identify his way of decision making, because what we also experienced was sometimes what we think they are using is the middle 0.25 millimeters, but what they are actually using is 0.3 millimeters because they have space. They have their room. They have no other requirements, and they just use it. It's even cheaper for them to use a 0.3 millimeter drill, and so they may use it, yeah. Which is, I mean, the problem is if we're using the bigger drill or the smaller drill, we are varying here, yeah. I want to be precise and not have anything, yeah. If we're coming to the next slide, which is also interesting, ask just tolerances, if they have tolerances on their Gerber files. For example, if we vary the pad diameter about 10% plus minus, then what does this effect have on our stub resonance? As you see, also almost 1 gigahertz back and forth. So if there's a tolerance, which is, I think, unlikely, but there may be a tolerance, always go with the as designed parameter here. On the same page, if we're looking at the anti-pad diameter, it's the same, plus minus 10%. We don't see that much deviation, but there's still deviation. And you should also go with the as designed value here. Yeah. Next, a very interesting thing are non-functional pads. What happens if we keep them there, and what happens if we remove them? So what you see on the left is a very strong deviation. The one with non-functional pads lands at 13.2 gigahertz. The next one 2 gigahertz above. And the interesting thing is, if we remove them, if the PCB vendor knows, okay, I shall remove them, then we can gain 2 gigahertz of bandwidth, of channel bandwidth effectively, which is quite nice. Yeah. And then another tolerance or fabrication tolerance that we have is the PCB thickness. What we give is a drawing plus minus 10%. It's the typical application. And if you see the effect, it's more than 1 gigahertz. So we almost have like 1.5 to 2 gigahertz of deviation plus and minus. So it's a very large deviation that we can have, but we do not have to have it. So yeah, it's sometimes, but sometimes not. If you want to take it to a worst case scenario, you would take the thicker one, because this moves your channel bandwidth to the left. So it reduces your channel bandwidth. But in typical cases, I would also stick with the drawing here. Yeah. So summarize all these parameters. The most important ones are, so they are listed here on the stub resonance in black, and the effect on the stub resonance. The orange one is the effect on the time, consuming. And the interesting thing is that the parameters up here, they are very sensitive to your stub resonance. You want to keep track of them, and you want to have control over them to know what to simulate and what you get in the end. So these are auto mesh, thickness tolerance, your non-functional pad removal, dielectric constant estimation, and also drill diameter. Yeah, pad and anti-pad may be effective, but yeah, I think it's not that critical. Yeah. If we have all these parameters set up correctly, working through them and trying to figure out with a manufacturer and all the other guys, what is our final PCB looking like, and we simulate this, then this is going to be our result. First of all, these are the parameters. I mean, we went through them. I will skip this foil. It's just for you to, and as an overview, what I used for the simulation. But the interesting thing is going back to the first channel that we have, which you see here, compared to the other ones. If you remember, They were like at 5 or 6 gigahertz and then at 16 gigahertz. Right now, we are very close to our measurement. So simulation measurement is very closely together, which is very nice. And also what is interesting that the curving is going to be quite nice. The next channel that we have is the same channel as before, just added one via again. Quite simple, but what does it do? What does it do if we have two via stubs of the same length? And what does hyperlinks do with it? What we see here is it's on the same resonance frequency again. And the interesting part is it's acting like a higher order filter or something like this, yeah. And if we go even further, if we add another via, we see like a third order filter, also with the same resonance frequency and also the same kind of like break off frequency point. Yeah, that's the main part of my talk. Like this was a specific example of what we did, but the main topic was actually how to, like this was just one example, how to get it into a standardized feature. Yeah, learning from this, building a constraint model or something like this, that we can, that we do this error once, but not every time. Yeah, and the first point of these process are understanding the problem. So what is causing the issue? It's a reduction of the channel bandwidth. Then what solver do we need? Yeah, up to, if we want to do it more accurately, we need the full-wave solver. And for this to get accurate, as I mentioned, you need to be aware in your mesh of non-functional pads and your drill size and the stub itself, but also have communication with your vendor and also with your design data. What are you sending? What is included? Was it not included? How does he manufacture? And how is your PCB manufactured with the pressing and all this stuff? And with this, you can create great digital twins of your dielectric PCBs. Thank you.
Is it possible to simulate type 7 vias, which are plugged with epoxy and recovered with a pad?
It's what we typically use, yes. Yeah.
What's about the impedance of the vias? Also simulating them? Is this another simulation you have set up?
In this range, I specifically wanted to isolate only the resonance, because like in our test channels, we didn't even have a through part of a via. It's just running on top and then only having a stub. But in total, the via impedance is very important to us, yes. We're also not only trying to estimate the via impedance itself, but also the effect of the remaining, even if it's a small stub, we're getting more capacitive loading and then reducing your impedance. So we always try to get a good approach with this, which is still applicable in PCB design. If you have large boards, FPGAs, large BGAs, then it's always a trade-off. So, for example, I know the 100 ohms are quite difficult to achieve, because it's like you have anti-pads that are huge most of the times, and so it's always a trade-off. Yeah.
Can I have another question? Because this brings me to my next question. I think I didn't understand it correctly. Why is your trace going over the via, not through the via? So
yeah, this is only for isolating. If you show this, like this channel, is the vias like here. You have only a trace with the perfect thing would be measuring and simulating right here to only get to not even get the effect of the trace. So I really want to isolate the effect of the stub resonance and how's the stub resonance affected by length and by capacitive loading.
Okay, got it. Thank you.
You're welcome.
More questions? How much time do you spend for this? Was the question. Yeah.
For this,
Yeah, because it's been quite a lot of runs and like 5 minutes per run or per frequency. So that's probably like, I don't know, a couple of weeks of simulations.
I can tell you, like the plots like this one, the interesting part is what I was also interested in is I use adaptive frequency sampling, and I simulated always up to 40 gigahertz, which we don't see right here. And I always had between 12 to 15 frequency points only in the total range, and then got a interpolation. And the interesting part is, I think, because 15 points up to 15 minutes, like this is the total maximum that I simulated. The interesting part is that the characteristic filter curve is still fit with only 15 frequency points. So it's quite interesting that there's a good match, a good I don't know, like a good understanding of interpolation, yeah, in there. Yeah, thank you.
Okay, I think there are no further questions. But yeah, for me, impressive, really impressive, because it has so many, besides the result, it has so many side findings, like the drill diameter. That was a really nice finding and helpful, and gives insight in this technology. Thanks a lot for pulling all this stuff together, and the applause is yours.
Yeah, thank you.
Mm.